Good morning. This is lecture 25, module 4, matrix analysis of structures with axial elements. In this session we will be completing the application of the reduced stiffness method. If you recall, in the last class we had shown how this can be applied to 1D systems and also plane trusses. We will do one more example of plane truss and then we will take a look at space truss. This is covered in the book Advanced Structural Analysis, Reduced Element Stiffness Method. Remember this diagram. This one way of seeing the big picture, seeing global coordinates, local coordinates, structure stiffness matrix, element stiffness matrix and the two transformations. In the stiffness method, especially the reduced element stiffness method, your first task is to get the TD matrix correct, and you remember we had some difficulty when we did the plane truss, but is it clear? Today I will show you an alternative way of doing it. Okay. Once you have got the TD matrix, you can partition it to TDA and TDR. If the problem does not require you to find support reactions and you do not have any support movements, then you can skip the TDR, it is enough to do TDA. So remember, this was a problem we solved at the end of the last class, and it took a while for you to get the idea of getting the TDA matrix using the kinematic approach, and we finally got this. You remember we did it step by step. This is actually a very efficient way of doing it because you can program it, you do not have to think, it will do it automatically, provided you are clear about the start node, the end node and the correct value of theta Ix. There is another way of doing this, can you tell me that? There is another, perhaps simpler, but then you have to solve every problem manually. What would that be? You can use a static approach. How do you do that? TD transpose. So you are actually invoking the contra gradient principle. Is it easier to derive the TDA transpose matrix than the TDA? Let us see. So in the static approach, this is the relationship that we want, right? Please note, in the kinematic approach what we are doing is we have the structure. In the structure we are applying one global displacement at a time, arresting all the other displacements, and then we are finding out what happens at the element level. If you look at the element displacement vector, what do these quantities refer to? These are the element displacements. The element, what do they refer to? What does D1 star refer to?
Axial deformation.
It is just the elongation in the element 1. This has only 1 degree of freedom. Is it clear? And so if you move the structure, the joint displacement one at a time, it is going to cause elongations in the different members, and we are trying to figure out what these elongations are. You apply, let us say you want to fill up the first column, you put D1 equal to 1. You can actually draw a sketch and figure out what the elongations are, or you can do it mechanically using the formula that we demonstrated in the last session, minus cos theta minus sin theta plus cos theta plus sin theta, right, for the sign convention we assume. We are now doing something different, something very interesting, and I want you to understand physically what we are doing here. Here we are actually, what is the size of the TDA transpose matrix for this problem? 5 into 6. So there are going to be 6 columns and 5 rows. Let us take the first one. Okay, I want to fill up the first column. That means I must apply F1 star equal to 1. What is F1 star? It is the bar force in element 1. So I must visualize a situation where in this truss only this bar will have a force. Do not ask me how that force comes. let us say somehow you have only one force, only one element has a force, no other elements have a force, then to satisfy equilibrium you must be having some joint forces, then only it is a self equilibrating system. So can you fill up the first column of this using equilibrium? Let me help you. So you need to look at only bar 1 because bars 2, 3, 4, 5, 6 do not have any forces. So will it not look like this? Will it not look like this? I mean I can draw the whole truss, but I might as well take it out separately. If that bar force in bar 1 has to be unity, then does not equilibrium demand that I must have equal and opposite forces at the two ends, and this refers to the coordinate 2 and this refers to the coordinate 8, right? And it follows that if this has to have a unit value, F2 must be equal to 1 plus 1 because 2 is pointing upward, and F8 must be equal to minus 1, agreed? And there are going to be no other values, no other forces in the truss. So help me fill up the first column. What will it look like? 0, 1, 0, 0, 0. Okay. Now what about this F8? Yeah, so if I want to include the restraint coordinates, then my size of my TD matrix will be bigger. I have to bring in TDR. Is it clear? Can you similarly fill up the next column?
1 0.
Well, that's a picture. 0 0 0 1 0. Got it? Third one.
0.6.80.
So third one. Okay. If I have to have a unit force in bar 3, I must have equal and opposite forces. So very clearly the component of this along the x axis must be given by this force, and the component of this along the y axis must be given by that force. And at this end I need not worry because it is going to a restraint coordinate. So is it clear F3 and F4 you will get like this, right? Now fill up the next one. I am not going to draw any more.
Minus 0.6, 0.8.
No, now you are dealing with this bar 4, bar 4.
0.6. Oh, minus 1 0 1 0.
Please do it and give me the answer. Well, take a look. In this bar, if it were to have a force, it will affect 1, 2, 5, right? 6 is outside. 1, 2 and 5. So what is F1 going to be?
Minus 0.6.
Minus 0.6. What is F2 going to be?
0.8.
Plus 0.8. What is F5 going to be?
0. 0.6. 0.6. 0.6.
If you can't do this, you are in trouble. Okay. It's easy. It's not difficult. Okay. Actually, you can generate using the kinematic approach, and you can do a quick check using the static approach. What about the next column? F5. That's pretty easy. That is, you are going to fill up. If this bar were to have a unit force, minus 1, 0, 1, 0, 0. Very good. You become expert at this. Last one, 6th column. The spring alone will have a unit force. So which you will get only here, right? 0, 0, 0, 0. Great. Got it? Now just check it out. Yeah. This row here in the TDA matrix is the column here in the TDA transpose matrix. You can check out all the rows. So which do you prefer, the kinematic approach or the static approach? That's because we have been brainwashed right from the beginning to study equilibrium. Engineers are very strong in, usually very strong in statics and very weak in kinematics, because kinematics needs a little more exercise of your brain. You have to physically see the movements. Statics is more abstract. Is it clear? But it's good to to know both techniques. But when you are programming, I think it is just blindly do it by the method we did it in the last class. Is it clear? Are you now absolutely clear about TD matrix? Not afraid of it? Comfortable with it? Imagine what you need to do in a space truss. It's really challenging. Okay, let's do a tough problem. This is a compound truss. Okay, we have done this remember in basic structural analysis. So we are now going to do it by stiffness method, by reduced element stiffness method. So how do we do it? Well, as a truss is statically determinate, how do we know it is statically determinate? You can also do that check m plus r equal to 2j. We know that the bar forces will not be dependent on the element stiffnesses. Let us say the question here is just find the bar forces, okay. So no need to find the joint displacement. So you have to assume the axial stiffness of all the members. If no input data is given to you, you can conveniently assume that all the bars have the same axial rigidity EA. Will this change the answer? Let us say every bar had a different EA. What will it change? What will change? The displacement field gets affected. The elongations in the bars will depend on the axial stiffness or axial rigidity. The joint displacement will get affected, but the bar forces do not get affected. Why? Because this is a statically determinate system. So we can make this assumption, and let us do that and go ahead. So we have to now put the global coordinates. How many active coordinates do you think we have here?
1, 2, 3, 4, 5, 6, 9.
Okay, so let us label them 1, 2, 3, 4, 5, 6, 7, 8, 9, very easy. We have some restraint coordinates also 3, 10, 11, 12, clear? Very easy. What do we do next? Local coordinates. Okay, you have to draw that sketch, and that is it, standard sketch. Every element can be modeled like this, and the axial stiffness is given by EA by L. In this case we are assuming EA is constant for all the bars just for convenience. Okay. How do we solve this problem? Exactly the same procedure as we did earlier. Generate the TDA matrix, which is what you are going to do now, and structure stiffness matrix. You can use the direct stiffness method and get, all you need is KAA here. You do not need to fill the whole matrix because we just want to find the bar forces. Very easy to do, as we are required to find only the bar forces and not the support reaction in this problem, and as there are no support movements, we can ignore the restrained global coordinates, and finally you get the member forces. This is all standard, right, as we did in the last problem. So here is another exercise for you. Fill up the TDA matrix with this help. Okay, now let us just see how we did this. This table is very helpful, especially for programming. There are 9 bars, so I call them 1, 2, 3, 4 all the way to 9, then bars are labeled here. I have to decide my origin, so let me say my origin is at A. Okay, so I write down all the coordinates A, B, C, D, E everywhere, and these dimensions are given to you, so it is pretty easy to write this down. Then I have to decide on my direction for X star. That means I must identify my start node and end node. So for example, bar 1 starts at A, ends at B, bar 2 starts at B, ends at C, bar 3 starts at C, ends at D, bar 4 starts at D, ends at E, and bar 5 starts at E, ends at F, right. I went sequentially. Then bar 6 starts at A, can you see it, starts at A, ends at D, and bar 7 starts at A, ends at E, bar 8 starts at F, ends at B, C, and bar 9 starts at F, ends at B. Is it clear? It is not difficult to do, in fact it is ideal for programming, and that is how you identify the joints, the nodes, and the elements and the direction of incidence. Now once you have done this, you just have to put in this formula, it will generate the length, right. Is this clear? This formula is straightforward. You do not have to do any calculations, it will do it automatically. So you will get all the lengths. Now bar 3 has a length 1 because it is 1 meter, but let it generate it automatically. So you can write a small program, it will do it. Similarly you can get cos theta and sin theta. Is this clear? You do not have to break your head over it, you can do it automatically. With this information, can you fill in the TDA matrix at least for element 1? For the first element, fill in the TDA matrix, and by the way you can also get the axial stiffnesses because it is given by EA by L. L you have got here, you have calculated L here, so it works out to these values here. Signs are interchanged?
The fourth one, cos theta should be positive.
Wonderful. Cos theta for the fourth element. Yeah, it is right, from the end to the start. So what does it work? What is the end? 4 minus 3, so it should be positive, right.
It's in the fourth quadrant, so it has to be positive.
Use your corrected values and let us get TDA. Give me TDA for element 1. Is the element 1 okay?
Yes, sir.
Okay, so
4 and 5 everything else.
except for 4 and 5 everything else is okay, wonderful. So 4 and 5 you correct it and you generate for element 1 only. You are right, the plus and minus got switched. Please get me the TDA matrix. Okay, so this is a formulation. So this can be easily generated. For example, take the element 1. The element 1 is connecting to 1 and 2 and something here, probably 10 and 11 here. 10 and 11 is outside TDA, right. So which is the start node? Start node is here. Which is the end node? End node is there. So you will be using cos theta and sin theta plus. And does it match? Is this correct? Let us just check. That is right, cos theta for this is this and sin theta for this is this. Is it clear? All the others will be 0. Like that it is possible to generate for all the other elements. Can you do it? Will you work it out? If there is an error in the 4th and 5th, you correct it. Okay, will you do it? Is it difficult? Can it be done easily? Okay, so let us proceed. I just want to demonstrate that you can do big problems as well just by programming and letting the computer generate all these results, but you can also manually do it. Okay, now you need to now pre-multiply the TDA matrix with the Ki star matrix. So that is easy to do. You have already got Ki star, because what is Ki star? Ki star is a 1 by 1 matrix, is given by EA by L. We have already done these calculations. So whatever values you got there, just multiply them. The first row in the previous TDA matrix you multiply with K1, second row you multiply with K2, so you will get these numbers, okay, right. It is easy to do. What do you do next? Again you pre-multiply all of these with TDA transpose. So you do that, you are right, you do that, you sum up over 9 elements and you will get the full structure stiffness matrix. Is it clear? You will get the full structure stiffness matrix, but if you make errors in the TDA with signs and all that, some elements in this matrix will have a wrong sign, okay. But you will notice one thing, all the diagonal elements will always be positive. So please do this carefully. better not do it manually, do it in MATLAB or Skylab or whichever software you have. Will you check this out? This is it's a demonstration of how you can do it for a big problem. Obviously such problems won't be asked in any examination because you just don't have the tools or the time to do it, but in real life you have such problems. And then what's your loading? Your loading is a force acting at B, and that coordinate matches with F2. So your loading is F2 is equal to minus P. Of course you can handle any loading, but in this problem we had just one isolated concentrated load. You have the stiffness matrix, you can invert it and don't bother to write it down, let the computer do it. Do double precision if you want so that you preserve the accuracy in the matrix, and just pre-multiply. Since you have a well conditioned matrix, the inverted value will be very good, inverted matrix will be very good. One way is to check it out, you do K inverse K, you should get an identity matrix with very minimal errors. Otherwise, if it is not so well conditioned, it is safer to use some elimination techniques, or you can even use Gauss elimination to do it, or Gauss Seidel. Those are all options that you have, but I think it is good enough to just do the matrix multiplication. So once you have done this, you have got the joint displacements. What do you do next? You got the unknown displacements. So then you get the member forces. Remember you had already calculated this KTdA, you got those calculations, just multiply them with dA and you will get the bar forces, and check them out with the answers we got when you did the same problem, because it is statically determinate. We use method of sections, they should match. That is your proof. The proof is you are checking with the force method and seeing whether you are getting the answers. So that is it, we have solved a very a problem that is easier to solve using the force method by the more difficult stiffness method, because the computer, the software will always do it by the stiffness method. So at least the method you are clear with in while solving plane trusses. Okay. You can check equilibrium by including the restrained global coordinates, you can also get the support reactions. It's easy to do, for want of space we are not doing it, but you will get the correct answer. Okay. Now let us jump into the most difficult problem of space trusses. One good thing is the same element stiffness matrix holds good whether you are dealing with a 1D structure, 2D structure or a 3D structure. The rank of that matrix is 1. All you need is the axial stiffness, but you have to worry about the orientations, because when it was a 1D system like a chain, you had just the x axis. When you had a plane truss, you had x axis and y axis. Now you have x, y and z, right. So the local coordinates do not change, but your TDA transformation changes. Can you visualize how it changes? For example, you are comfortable with a plane truss, you know it is going to be, if you are trying to link the joint displacements at the two ends with the axial deformation the element, it is always related by this minus cos theta, minus sin theta, plus cos theta, plus sin theta. How do you think this will look when you are dealing with an element arbitrarily directed in space? Will you use cos theta and sin theta? Are there more thetas than one theta? How many thetas do you need to do? There are 3 thetas. Let us say I have a vector in space, I have x coordinate, y coordinate and z coordinate. Okay. I have 3 thetas, but they are related by the norm that the direction, that is right. Cos squared theta x plus cos squared theta y plus cos squared theta z must be equal to 1, right. And is it difficult to get the cos theta sin theta? No, once you have the coordinates you do the same game. Can you guess? Can you guess what will be the TD matrix.
Plus
And?
cos theta x plus cos theta z plus
Brilliant. So you hit the nail on the head. That's all. That's all. Okay. So for a space truss, write down the 3 direction cosines. Okay. You don't have to write theta also. You just need the coordinates, because this is actually cos theta x, cos theta y, cos theta z. And then just like you had minus cos theta minus sin theta, by the way, minus sin theta is actually a direction cosine with respect to the y axis. So you need the 3, the x axis, y axis and z axis, and you have minus. Why is it minus on for the first 3 and plus for the next 3?
start node and
Because if you are looking at this corner, I have not drawn a picture, you have 1, 2, 3, you will find that you are pushing the element inwards. So the element is going to contract, whereas at the other end you are pulling the element outward, so it is going to elongate, right. That is why in the first place these were minuses and these were plus, and the same argument holds good here. You have a doubt? Yes. Okay. Let me explain. This is your element, right. Let us do the plane thing first, plane truss. Maybe you should be looking like this, right. So this was your x axis, this was your y axis, right, and your coordinate was 1 and 2, and you had coordinate 3 and 4, right. Now we want to know what happens when I apply d1 equal to 1 to this element and d2 equal to 1. Do you agree? When I apply d1 equal to 1 and I prevent this movement and I prevent d2, this is going to reduce in length because I am pushing it. So what do will I get a positive elongation or a negative elongation? So whether I push it this way or this way, I am going to get minus, but whether I pull it this way or this way, I will get this member elongating plus. Does it make sense now? At the start node for the directions we assume you will get minus minus plus plus. Now what has happened is this is now tilting in space, it is pointing like that. So I have not only x, not only y, I have z. So I have 3 coordinates, 1, 2, 3, and whether I push, whichever way I push, as long as I arrest this degree of freedom and the other 2 degrees of freedom, I will always get a contraction, and when I pull here I get an elongation. Does it make sense? That is all you need to know. Okay. Now if you are doing conventional stiffness method, which we briefly discussed, it is a little more complicated, but in reduced element stiffness method it is pretty easy. Clear?
Tension coefficient method only applicable for just rigid structure, statically determined.
You tell me.
no, it's
What is
it
the
can be
tension coefficient method? It is just writing down equilibrium equations from joint to joint.
And it did involve direction cosine.
It did involve direction cosine because your forces have components in all the 3 vectors. Actually you have direction, but you have got a certain number of equations, you are not looking at compatibility. So obviously it is applicable only for a statically determinate just rigid structure. Luckily for us, most of our trusses, including transmission line towers, are by and large statically determinate. Okay. You can also program it, it can be done, but a standard software packages does not, because it wants to handle both the determinate and the indeterminate. It will do, your degree of static indeterminacy may be 0 or 1 or 2, the degree of kinematic indeterminacy may be 50 or 100. It will still prefer to solve 100 simultaneous equations because it is programmed that way. Otherwise you have a choice about your redundant. Is it clear? Okay, let us take a simple problem, and I want you to do it intuitively. You could be asked this problem even in your IIT entrance exam. So I am going back to school giving you a simple problem. Consider a simple space frame comprising 3 identical members in a tripod arrangement. Remember you have been using the theodolite, So it has got 3 legs, let us say you keep it symmetrically, okay, and you have got a weight hanging from the ball and socket joint at the top. Each leg is 2 meters long and interconnected to a ball and socket joint at O at top 1 meter above ground, with their hinged bases forming an equilateral triangle on level ground. Now I have seen you people put some triangle there so that it does not move in the corners, no, when you use the theodolite. That is as good as providing a hinged base, otherwise you have to plant it firmly on the ground so that it does not move. Show how the stiffness method can be used to find the axial force in the 3 members when the joint at O is subject to a gravity load of 60 kilonewton. Also show that no axial force will be induced in the members on account of any lack of fit or temperature effects. Why won't you have any axial forces? Because it is a just rigid statically determinate structure, but we have to demonstrate it using stiffness method. It is a simple problem, so let us give it a shot. Here is a plan view, okay, I have done the work for you. Here is a side elevation, say section VV. Can you understand what is going on? It is a triangle on the base, it is arrested here, arrested here, arrested here. They are pinned, suppose this O is above, it is 1 meter above, right. A, B and C are restrained and I need to find, I forget about the restraint coordinate. So I have only 3 active degrees of freedom. Let me call them 1, 2 and 3. Does it make sense? A tripod 1 up, 2 along the x axis and 3 along the z axis. I have chosen this point B as my origin, this is x, this is z, y is vertically above, okay, this is y, got it? Is this picture clear? And you can figure out how to locate these dimensions, because you are given this length is 2 meters, so if this is 2 meters you can, this angle will be 30 degrees because this is 2 and this is 1, so 1, 2 and this will be root 3, so this is 1.732. So these dimensions can be worked out, okay, that is the first thing you need to do. Now without doing any calculations except extremely simple ones, can you tell me what is the force in each of these legs? Will the forces be equal? Yes, tell me the value. The total weight is 60, so 60 divided by 320?
No sir,
Come
no
on.
sir.
How do you get it? Common sense, how do you get it? The vertical component
is 30.
of the axial force in the bar must, each bar must be 20, 40 in each. Is it clear?
Yes sir.
Okay, let us see. So first of all it is statically determinate, you have 3 members, you have 4 joints, it is restrained in 3 directions, so m plus r equal to 3j. It is symmetric, so all the 3 bars will have the same axial compressive force N, and 3n plus 60 is equal to 0, so N is 20 by sine theta, and theta you can show it turns out to be 30 degrees, and so it is 40. You are right, that is how easy it is. But let us pretend we do not know the answer and we have to do it the hard way using the stiffness method, okay, it is an easy problem. So the procedure is as we did in the previous example, but we are dealing with a space truss. This is our truss. Here again we will, for the coordinates chosen, it is possible to write the start node, the end node, the CIX, CIY and CIZ, okay, clear? You can do it, okay. Then the start node is arrested in all the 3 legs, so the active coordinates are at the end node, so the minus 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 is not required here, only plus plus plus. Is it clear? So that is easy to write down, so you can pick that out, and that is what you get, okay. So you just have to pick the values we got from the previous table you have got your TDA matrix, it is straightforward, there is nothing in it, right. Then what do? You have got your TDA matrix, then you have to generate your stiffness matrix. How do you do that? Well, let us assume all the 3 legs are identical, same EA value, the length of each is 2 meters, so EA by 2. So I can put it in the unassembled form, EA by 2, EA by 2, EA by 2, 1 by 2 is 0.5, so I can write like this, clear? This is my K tilde star matrix. Then I do the same thing as I did earlier, I post multiply by TDA, I have got TDA, what is TDA? This direction cosine matrix, and I have got K star, and so I get this. Then what do I do with this? Pre multiply by TDA transpose. So let the computer do all that, you have got this. When you see an answer like this, you should pause a while. Why? Why should you pause? You should think if you are a good engineer, because you have got a diagonal matrix which is rare. Did you make a mistake or does it make sense? Can you? So you have to always pause whenever you get beautiful results, you must say, why didn't I figure it out? Is there some meaning? So let us see carefully. Well, first thing, you have this tripod, if 2 is acting upward, right, it is symmetric. So if I arrest 1 and 3 and pull up 2, do you think where I have arrested there will be some reactions, because they will be K12 and K32, or there is no need to arrest, those points are not going to move. What do you feel? It is symmetric. When I pull something up, will it have any displacement in the horizontal plane? No. So it makes sense. So you have proved intuitively that K12 and K32 will be 0. So that proves something. Okay, now you apply K, you put a force F D3 equal to 1, put a displacement D, you pull it, okay. Do you think vertically there will be any movement?
No.
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 So you won't get a force K23, you won't get a force K23, agreed? Because vertically there won't be any reaction. And sideways, will it be partial to one side? No. So you get K13 equals 6. So intuitively you know, yes, it is going to be a diagonal matrix, and so it makes sense. Is it clear? It is good to do these checks. Then you find the equivalent joint loads, you get, is this correct? The loads are 0, minus 60, 0. Okay, then what do? Now let us add some more masala to this problem. We will say, let the bars have lack of fit. We want to show that the answers remain 40, 40, 40. So let's make it arbitrary. Let us say the 3 bars, either lack of fit or temperature effects, you have some initial values E01, E02, E03, fine. Now what will this cause in terms of forces? I will get fixed end forces. How do I find them out? Well, just multiply it by minus K, right. I will get a compression and it is this value, agreed. Then I have to shift this to the, please pay attention, we moved ahead, that you can sort out later. You have to find the joint forces. How do we do that? TDA transpose. So you multiply this out, you get some forces. So these are forces in terms of arbitrary E01, E02, etc. You need to prove that these forces are not going to add to your member forces, and it's a great proof if you can do that. So let us see how to do that. So let us get the answers now. You have got your load vector now. So I have inverted my K matrix, it will look like this, very easy to invert because it is a diagonal matrix. This is my load vector FA, and this is my fixed end force vector with a minus sign with all that arbitrary E01, E02, E03. When I actually do this multiplication, I will get some displacements, okay. I will get definitely there will be displacements caused by these lack of it issues. So I will get dA, I will get d1, d2, d3. Now what should I do with these answers? Put it back and get the bar forces, and that is what you will do, and hey presto, you do not get E01, E02, E03, they cancel out, you get only minus 40, minus 40. This is a fantastic proof that in just rigid systems indirect loading does not induce any, does not change the force field, okay. It is a good demonstration. So the reason is the structure is just rigid. Now this is a reading exercise, I put a star there. This is a complicated space truss. The triangle DEF is horizontal, but at this height 10 meter above ground. The triangle ABC is at the ground level, and you have got all these bars connecting them in space. I think we have done this problem by tension coefficient method. You have done it earlier last year, right? Can you do it by stiffness method? Because if you can do this problem, you can do any problem, because this is a small transmission line tower, the real one will be huge. So if you can program this, you have done it, but this is something I leave it and just find the bar forces. You can put the support restraints, you will find it statically determinate, okay. This is a reading exercise for you, you can go back to the book, it is a solved problem. Can you see the 3D picture? So you have to identify the direction of incidence of all the members. You have 18 global coordinates. This problem can be solved, and actually we have solved it, it is demonstrated in the book, just go through it. Not to worry, in the exam we are not going to certainly ask you these problems, but it is good, those of you who are interested, you know that you can handle any problem by this method. So with that we have finished the reduced element stiffness method. I hope you have got a good grasp of it, okay. Only one topic left, flexibility method. We will go through it fast, because really speaking matrix method using flexibility method is not good for programming, especially if we have intermediate loads, but still we should know the concept behind it, so we will cover it in the next class. Thank you.